Welcome to this problem walkthrough. Today, we'll explore the problem titled Maximum and Sum of Array, which is an interesting challenge involving bitwise operations and optimization strategies. Let's dive in to understand the problem and solve it step by step. In this problem, we are given an integer array nums with a length of n and an integer number slots. The key condition here is that the number of slots, which is specified by number slots, must be sufficient to hold all the numbers, meaning that 2 asterisk number slots must be greater than or equal to n. Each slot can hold up to 2 elements. The challenge lies in placing the numbers into the slots in a way that maximizes the n-sum. The n-sum is calculated by taking the bitwise n of each number with the slot number it is placed in and summing up these contributions. For example, if a number from the array is placed in a slot, the contribution to the n-sum is the result of nums, I, and j, where j is the slot number. The task is to determine the maximum possible n-sum for the given input. The constraints are such that the numbers in nums can go up to 10 to the power of 8, and the maximum number of slots is 9, making the problem computationally feasible. The output should be an integer representing this maximum n-sum. To understand this better, let's consider the first example. Here, the input array is nums equals 1, 2, 3, 4, 5, 6, and we are given number slots equals 3. The goal is to distribute the 6 numbers among the 3 slots, with each slot able to hold up to 2 numbers. One optimal placement is as follows: place 1 and 2 in slot 1. The contributions from these placements are 1 and 1 equals 1 and 2 and 1 equals 0, respectively. Then, place 3 and 4 in slot 2. Their contributions are 3 and 2 equals 2 and 4 and 2 equals 0. Finally, place 5 and 6 in slot 3, with their contributions being 5 and 3 equals 1 and 6 and 3 equals 4. If we sum these contributions, we get 1 plus 0 plus 2 plus 0 plus 1 plus 4 equals 9. This is the maximum n-sum achievable for this input configuration. Now, let's look at another example. In this case, the input array is nums equals 1, 3, 10, 4, 7, and the number of slots is number slots equals 2. The challenge remains the same, to distribute the numbers across the slots to maximize the n-sum. One optimal way to do this is by placing 1 and 3 in slot 1. The contributions are 1 and 1 equals 1 and 3 and 1 equals 1. Then, place 10, 4, and 7 in slot 2. Their contributions are 10 and 2 equals 2, 4 and 2 equals 0, and 7 and 2 equals 2. Adding these up gives a total n-sum of 1 plus 1 plus 2 plus 0 plus 2 equals 24, which is the maximum possible for this configuration. Finally, let's summarize some constraints and edge cases for this problem. The constraints specify that the length of nums must be between 1 and 2 asterisk number slots, while number slots can range from 1 to 9. Each number in nums can go up to 10⁻8. In terms of edge cases, if there is only one number in one slot, the n-sum is simply the bitwise n of that number with 1. For the maximum input size, where n equals 2 asterisk number slots and the numbers are large, the algorithm must remain efficient. If all numbers in nums are 0, the n-sum will always be 0. Additionally, if there is only one slot, all numbers must be placed there, and the n-sum will be the sum of nums, I, and 1 for all elements in the array. These considerations highlight the importance of designing an efficient solution that works under all possible conditions. To tackle the problem of maximizing the n-sum of an array, we need to strategically assign elements from the array nums into a set of slots, called number slots. Each slot can hold up to 2 numbers, and our goal is to maximize the sum of the bitwise n operation between each number and the index of the slot it is placed in. This setup leads us to evaluate different approaches. The first approach is brute force. Here, we consider all possible ways of assigning numbers to slots. For each assignment, we calculate the sum of the bitwise n values. While this method is conceptually straightforward, it suffers from exponential time complexity. With number slots and a maximum of 2 numbers per slot, the sheer number of possible assignments grows rapidly, making this approach impractical for larger inputs. Its feasibility is limited to small test cases where we can afford to explore every combination. A more sophisticated approach involves dynamic programming combined with bit masking. The idea here is to systematically explore partial assignments of numbers to slots by defining states that represent which numbers are already assigned. We use a bit mask to encode this information compactly. Specifically, we define dp mask j, where mask represents the set of numbers already assigned, and j tracks the number of slots processed. Transitions between states occur as we try assigning unassigned numbers to available slots, updating the bit mask and contributing to the total in sum. This approach avoids recomputing overlapping subproblems, significantly reducing redundant calculations. The complexity is governed by the number of bitmask states, which is O, 2 to the power of n, and the number of slots, which is O, number slots. Although this method is more computationally intensive than a greedy heuristic, it ensures correctness by exploring all valid assignments. Greedy methods, on the other hand, prioritize high contribution assignments early on but often fail to find the optimal solution due to their short-sighted decision-making. While faster, greedy approaches are less reliable for this problem. Ultimately, we chose the dynamic programming with bit masking approach for its ability to guarantee optimality. Unlike the greedy method, which risks missing the best solution, DP systematically explores all possibilities while reusing results from overlapping subproblems. This makes it far more efficient than brute force while still ensuring the correct answer. The bitmask representation also allows us to scale the solution to larger input sizes by encoding states compactly. One key observation that guided this approach was recognizing that the order of assignments affects the result. By breaking the problem into smaller, manageable subproblems using states, we were able to simplify the process of exploring assignments. A critical insight was that each slot can hold up to 2 numbers, and the bitmask representation ensures that we adhere to this constraint while efficiently navigating the solution space. This balance of optimality, efficiency, and scalability makes DP with bit masking the clear choice for solving this problem. Every approach comes with trade-offs, and dynamic programming with bit masking is no exception. While it guarantees the optimal solution by systematically exploring all possibilities, it requires higher memory usage compared to the greedy method. This makes it suitable for scenarios where correctness is critical and computational resources are available. On the other hand, the greedy approach is faster and simpler but sacrifices optimality, making it more appropriate for approximations or when time is a significant constraint. Brute force, while conceptually simple and useful for validating the correctness of other methods in small test cases, becomes computationally infeasible as input sizes grow. By weighing these trade-offs, the DP approach with bit masking stands out as the best strategy for this problem, striking a balance between optimality and efficiency while remaining scalable to larger inputs. To solve the problem maximum and sum of array, we need to approach it systematically with a clear plan. The goal is to assign elements from the array nums to number slots in such a way that the overall sum of bitwise and operations between each number and its assigned slot index is maximized. Each slot can hold at most 2 numbers, which introduces constraints we need to respect. First, let's analyze the problem. The input consists of an array nums with n elements and an integer number slots. The output is the maximum possible sum of these n operations across all valid assignments. The key operation here is the bitwise AND, denoted by AND, which computes the bit-by-bit intersection of 2 numbers. To solve this efficiently, we use dynamic programming. The state is defined as dp mask, where mask is a bit mask representing which slots are currently occupied. Each bit in the mask corresponds to a slot, and the value of dp mask represents the maximum and sum achievable by assigning numbers according to that mask. This allows us to track assignments while ensuring we don't violate constraints like overfilling slots. We start by defining the base case for our dynamic programming approach. When no numbers are assigned, which corresponds to mask equals 0, the n sum is 0. Thus, dp 0 equals 0. From there, we derive the transition function. For any given state mask, we determine which numbers from nums have already been assigned based on the bits set in the mask. For each unassigned number, we evaluate all possible slots it could be assigned to. For a number nums, j, and an available slot, we compute the n value of the number and the slot index. This value is then used to update a new dp state, represented by new_mask, which is derived from mask by marking the slot as occupied. The transition formula is dp new_mask equals max dp new_mask dp mask plus nums j and slot_index. This ensures that we are always considering the optimal assignment for each state. To compute this efficiently, we process all mask values in ascending order, ensuring smaller masks are handled before larger ones. This allows us to build up solutions incrementally without revisiting redundant computations. The final answer to the problem will be the maximum value in the DP array after processing all possible masks. This represents the best possible and sum across all valid assignments. There are a few key insights to note. First, the use of bitmask representation is crucial, as it allows us to efficiently track slot assignments and verify constraints, such as ensuring no slot holds more than 2 numbers. Second, dynamic programming provides a way to optimize the solution by reusing prior computations, which is far more efficient than attempting to brute force all possible assignments. Third, it's important to remember that slot indices are 1-based, so we must handle this correctly when performing the in operation with the numbers. In terms of data structures, the dynamic programming array DP is of size 2*2* number slots, since it represents all possible states of slot assignments. Bitmask manipulation using bitwise operators is essential here, as it enables efficient encoding and decoding of these states. Now, let's analyze the complexity of the algorithm. For time complexity, there are 2*2* number slots, possible states in the DP array. For each state, we process up to n numbers and consider assignments to number slots. This gives us a total time complexity of 2*2* number slots, *n* number slots. For space complexity, the primary cost is the DP array itself, which requires 2*2* number slots, space. When dealing with edge cases, several scenarios need to be considered. For small inputs, such as when nums contains only one element, the solution simply involves assigning the number to the slot that yields the maximum in value. For cases where number slots is large relative to n, we must ensure that the algorithm adheres to the constraint of no more than 2 numbers per slot. Additionally, we must handle cases where the array nums contains zeros, as the in operation with 0 always results in 0. For example, given the input nums equals 1, 2, 3, and number slots equals 2, the algorithm must calculate the best possible assignments while respecting these constraints. The execution of the algorithm starts with initializing the DP array. We set DP 0 equals 0, representing the base case where no numbers are assigned, and initialize all other DP mask values to -infinity to indicate unprocessed states. We then iterate through all possible masks. For the mask 0, we can assign nums 0 equals 1 to slot 1, resulting in DP 10 equals 1 and 1 equals 1. Alternatively, assigning nums 0 equals 1 to slot 2 gives DP 100 equals 1 and 2 equals 0. This process continues for all masks, updating states as described by the transition formula. Finally, after processing all masks, the maximum value in the DP array represents the result. For the example input nums equals 1, 2, 3, and number slots equals 2, the algorithm outputs a maximum and sum of 3, achieved through an optimal assignment of numbers to slots. This illustrates how the dynamic programming approach efficiently finds the solution while adhering to the problem's constraints. This Python implementation solves LeetCode problem number 2172, maximum and sum of array, using dynamic programming with memoization. The problem involves assigning elements of the array nums into number slots, where each slot can hold up to 2 numbers, to maximize the sum of bitwise and operations between the numbers and their slot indices. The solution uses a helper function DP, slot_mask, where I is the index of the current number in nums, and slot_mask is a bit mask representing the number of elements already placed in each slot. Slot_mask uses 2 bits per slot to track whether 0, 1, or 2 elements have been placed in that slot. The DP function is memoized using @row_cache, none, to optimize performance, avoiding redundant calculations for the same state. The base case is when I equals n, meaning all numbers have been assigned, and the maximum sum is 0. For each number at index I, the algorithm iterates through all slots. Slots are indexed from 1 to number slots. It calculates the count of elements already in the current slot by extracting the relevant bits from slot_mask. If the slot has space for another number, i.e., count 2, it updates slot_mask to reflect the placement of the current number in this slot and recursively calculates the maximum sum for the next number. The bitwise in of nums, I, and the slot index is added to the result. Finally, the function returns the maximum sum obtained by considering all valid slot assignments. The bit mask-based approach ensures that the algorithm is efficient, with a manageable state space given the constraints of the problem. This implementation is complete, handles all edge cases, and adheres to the problem's requirements. Here, we begin the implementation of the solution in Java. First, we define a class named solution and implement the method maximum_a_and_dsum. This method takes in the array nums and the integer number slots, which represent the elements we need to assign to slots and the number of slots available, respectively. Inside this method, we initialize n as the length of the nums array and create a dynamic programming array dp of size 1, 2 number slots. This size accounts for all possible states of slot assignments, as each slot can hold up to 2 numbers. The dp array is filled with -1 to indicate uncomputed states. Finally, the method calls a helper function, passing in the nums array, the number of slots, the current index I initialized to 0, the slot mask initialized to 0, and the dp array. The helper function will recursively calculate the maximum and sum. Within the helper function, we first check if the index I is equal to the length of the nums array. If true, it means all numbers have been assigned to slots, so we return 0 as the base case. Next, we check if the current state, represented by slot mask, has already been computed in the dp array. If it has, we return the pre-computed value. The maxsum variable is then initialized to 0, representing the maximum and sum for the current state. We iterate over each slot from 1 to number slots, calculating the number of numbers currently assigned to the slot using a bitwise operation on slot mask. If the slot can hold more numbers, we calculate a new state, new mask, by adding the current number to the slot. Then, we recursively compute the maximum and sum for the next index I plus 1 with this new state, updating max sum if the current sum is greater. After completing the loop, we store the result for the current slot mask in the dp array and return max sum. In this problem, our goal is to maximize the sum of bitwise and operations between numbers from the array nums and slot indices, under the constraint that each slot can hold at most 2 numbers. To solve this efficiently, we use dynamic programming with bit masking. Let's consider an example where nums is 1, 2, 3, and the number of slots is 2. Here, the length of the array nums is 3, and the recursive function we use is dp, I, slot_mask, where I represents the index of the number we are currently placing, and slot_mask encodes the state of the slots. Initially, we start with I equals 0 and slot_mask equals 0, meaning no numbers have been placed yet and all slots are empty. At the first state, dp, 0, 0, we are placing the number nums, 0, equals 1. We iterate over each slot, starting with slot 1. For slot 1, we calculate the count of numbers already in the slot using slot_mask 0 and 3, which gives 0 since the slot is empty. Placing 1 here adds 1 and 1 equals 1 to the sum, and we make a recursive call to dp, 1, 1, to continue. For slot 2, the count is similarly 0, so placing 1 here adds 1 and 2 equals 0 to the sum, and we make the recursive call dp, 1, 4. Now, at state dp, 1, 1, we move to the second number, nums, 1 equals 2. Again, we iterate over the slots. For slot 1, the count is slot_mask 0, and 3 equals 1, meaning one number is already present. Adding 2 here gives 2 and 1 equals 0, and we make the call dp, 2, 2. For slot 2, which is still empty, placing 2 adds 2 and 2 equals 2 to the sum, leading to the call dp, 2, 5. At state dp, 2, 5, we are placing the third number, nums, 2, equals 3. For slot 1, the count is slot_mask 0, and 3 equals 1, indicating one number is already present. Placing 3 here adds 3 and 1 equals 1 to the sum, and we call dp, 3, 6. For slot 2, the count is slot_mask 2, and 3 equals 1, so placing 3 here adds 3 and 2 equals 2, and we call dp, 3, 9. Now, the base case is reached when I equals 3, meaning all numbers have been placed. At this point, the function returns 0 as there are no more numbers to process. After reaching the base case, we backtrack and combine the results of all recursive calls to calculate the maximum and sum for the given configuration. In this example, the result is dp, 0, 0, equals 4, which is the maximum and sum achievable. With this example complete, let's explore another scenario with a new input. In this new example, we have nums equals 5, 6, and number slots equals 2. The recursive function begins at dp 0, 0. Here, we are placing the first number, nums 0 equals 5. We iterate over the slots, starting with slot 1. Placing 5 in slot 1 adds 5 and 1 equals 1 to the sum, and we make the recursive call dp 1, 1. For slot 2, placing 5 adds 5 and 2 equals 0, and we make the recursive call dp 1, 4. These recursive calls will now process the next number in the array. At state dp 1, 1, we are placing the second number, nums 1 equals 6. For slot 1, the count is slot_mask 0, and 3 equals 1, meaning one number is already present. Placing 6 here adds 6 and 1 equals 0, and we call dp 2, 2. For slot 2, which is empty, placing 6 adds 6 and 2 equals 2, and we call dp 2, 5. At this point, we reach the base case when I equals 2, and the function returns 0 since all numbers are placed. Combining the results from all recursive calls, we calculate the maximum and sum, which for this example is dp 0, 0 equals 3. Key insights for this problem include the use of bit masking to encode slot states, recursion to explore all valid placements, and memoization to avoid redundant calculations. These techniques ensure the algorithm is efficient, especially for small values of number slots, where pruning through slot_mask constraints significantly reduces the search space. Here, we analyze the time complexity of the dynamic programming solution. The dp function depends on two key parameters, I, which tracks the index in the array nums, and slot_mask, a bit mask that encodes the state of all slots. Since I ranges from 0 to n, and the bit mask has two asterisk number slots bits, the total number of states is determined by combining these two factors. Specifically, there are n possible values for I, and 4 number slots possible configurations for the bit mask, since each slot can be in one of 4 states. Multiplying these together gives us the total number of states, which is n asterisk 4 number slots. For each state, we iterate through all the slots, checking if a slot can accommodate another number, updating the bit mask, and performing a recursive call. This work is proportional to number slots, giving us a transitions per state factor of number slots. Now, combining the total number of states with the transitions per state, we arrive at the overall time complexity of n asterisk 4 number slots asterisk number slots. Shifting focus to space complexity, the recursive nature of the dp function means the call stack can grow to a maximum depth of n, corresponding to the number of elements in nums. Additionally, the memoization table, enabled by row_cache, stores results for all distinct states, I, slot_mask, which are n asterisk 4 number slots, in number. The bit mask itself uses 2 asterisk number slots bits, but this is negligible compared to the size of the memoization table. Consequently, the overall space complexity is dominated by the memoization table, resulting in n asterisk 4 number slots. To highlight the efficiency of the dynamic programming solution, consider a naive approach where all permutations of nums are generated and distributed across number slots. Each slot can hold up to 2 numbers, leading to a total configuration count governed by factorials and combinatorics, such as n slash k1 asterisk k2 asterisk asterisk kn. This results in exponential complexity, which becomes infeasible for large inputs. In contrast, the dynamic programming solution avoids redundant calculations, leveraging memoization to systematically reduce the computational burden. While still exponential in number slots, the optimized complexity of n asterisk 4 number slots asterisk number slots is far more manageable compared to the brute force method. In terms of edge cases, the best case occurs when number slots is very small, such as 1 or 2, where the constants involved are reduced. However, the average and worst cases remain consistent with the derived complexity, as the exponential growth is tied to the number of slots and the structure of the input. The mathematical reasoning behind the time complexity centers on the exponential growth driven by 4 number slots. Each slot contributes 2 bits to the bit mask, and with number slots, this results in an exponential number of states. However, this growth is tempered by the linear dependence on n, the size of the input array, and number slots, which is the number of slots processed per state. This balance makes the solution efficient within the constraints of the problem. By leveraging memoization, the algorithm avoids redundant computations, ensuring that resources are used effectively. Overall, the solution strikes a balance between time and space efficiency, achieving an optimized approach to tackling the problem while managing the exponential state space. Now, let's begin by discussing some common mistakes to avoid when solving this problem. First, misunderstanding slot indexing is a frequent issue. Many developers use one-based indexing for slot indices, but the problem usually specifies slot indices starting from 1. This means that calculations like number and slot underscore index will yield incorrect results if you mistakenly adopt zero-based indexing. Be mindful of this to prevent subtle bugs in your logic. Another common mistake is relying on greedy assignment without backtracking. While it might seem efficient to assign numbers to slots greedily, this approach often overlooks optimal solutions that require revisiting earlier decisions. To maximize the end-sum, you need a strategy that explores different combinations, not just the first feasible choice. Finally, ignoring slot capacity is another pitfall to watch for. If the problem specifies a maximum of 2 elements per slot, exceeding this limit violates the constraints and leads to invalid results, or even runtime errors. Always double-check that your assignments respect these constraints to ensure your solution is valid. Another critical area to focus on is optimizing your recursion. One mistake is relying on plain recursion without memoization or dynamic programming. This leads to exponential time complexity, specifically O(2 to the power of n), which becomes infeasible as the input size grows. Memoization or dynamic programming helps store intermediate results, significantly reducing redundant calculations and improving performance. Equally important is defining a proper base case for your recursive function. An improper or missing base case can cause recursion to terminate prematurely or, worse, result in infinite loops that crash your program. A well-defined base case is essential for ensuring your recursion behaves as intended and produces correct results. These optimization techniques not only improve the efficiency of your solution but also demonstrate a solid understanding of recursion and dynamic programming principles, which are highly valued in technical interviews. When approaching this problem, it's helpful to view it through the lens of interview insights. For example, this challenge can be thought of as a variation of the knapsack problem, where elements, like weights, are assigned to bins or slots, but with additional constraints. Showing your understanding of combinatorial algorithms is a great way to impress interviewers. It's also important to highlight how you use memoization or dynamic programming to optimize recursive solutions. Interviewers often evaluate your ability to balance correctness with efficiency. Additionally, be prepared to discuss the trade-offs between backtracking and dynamic programming. While backtracking can work for small inputs, it becomes inefficient as the input size grows, making optimization necessary for larger cases. Don't forget to address edge cases, such as when all numbers in the array are zeros or when the number of elements far exceeds the number of slots. Finally, connecting this problem to related problems like partition to k equals some subsets or matchsticks to square not only showcases your problem-solving breadth but also reinforces your ability to recognize patterns across challenges. Let's wrap up by exploring some alternative approaches to solving this problem. The brute force approach involves trying all possible assignments of numbers to slots and calculating the total and sum for each configuration. While this method is simple to implement, it's computationally expensive, with a time complexity of k to the power of n, where k is the number of slots and n is the number of numbers in the array. This makes it impractical for larger inputs. A more efficient option is the dynamic programming approach. Here, you define the state based on the numbers already assigned in the current slot configuration, transitioning between states based on the end-sum. This approach is much faster, with a time complexity of n*2 to the power of n, but requires careful attention to detail when encoding and managing state transitions. Finally, a greedy approach combined with backtracking can offer a middle ground. This method uses a heuristic to assign numbers to slots and then backtracks when encountering suboptimal solutions. While faster than brute force, it can miss the optimal solution if the heuristic isn't robust enough. Weighing these options and understanding their trade-offs is key to selecting the right approach for the given constraints and input size. Great job! We've successfully tackled the maximum and sum of array problem using a dynamic programming approach. Remember, understanding the problem constraints and leveraging the right data structures is key to solving challenges like these. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!